Here we go. Okay, sorry, just want to get back to my lesson. So this is, I just want to say from the get-go that this lesson is primarily from the SciPy Lectures website. So if you go to the website, you can check it out. They have a lot of different lectures on how to use scientific Python packages. So they might have lectures on plotting, lectures on probability, lectures on statistics, lectures, all the different things you can think of for statistical Python, scientific Python. And I'm basing this lesson on the content that is there. So the first thing we're going to do, because we're thinking that we're working with some data and we want to run some statistics on it, right? So we want to import and explore our data. So the first thing I'm going to do is import a package that will let me import my data. So let's import Pandas, which is our package that will read our data frame or our CSV, Pandas as PD. And I'm just going to do a magic command that lets me show my plotting within my Jupyter Notebook. If that's what you're using right now, you can actually show your images in line with your code by having this command, which is matplotlib, and that's a percentage sign. So matplotlib, no space.
It's a magic function?
It's a magic, I can't remember if it's a magic function or a magic command. I don't know what the exact name is. Yeah, exactly. So it's recognized by by IPython, basically. So matplotlib inline, which will say that all the images will be in line with my code, and otherwise it won't actually appear. It's kind of like this weird little thing with Jupyter Notebook. So I'm going to run that, and you can run that with Shift-Enter. So I already have these cells made, right? But if you need to make a new one, Shift-Enter should give you a new cell also, and Command-Enter will just run it. So I have here Shift-Enter, and if you want to make new ones, you can press B. So I'm pressing B to make new ones. So just a little refresher on how to use these. Okay, so I've imported my packages. Everyone good so far? Okay, so what we're going to do is actually get our data. So I'm going to go back to that, to the website that let me, where all the links are. Okay, so I'm just going to copy the first link. So just copy it. And then I'm going to use that to read in my data. So a couple of things. We'll see. We're going to name it data is equal to, I'm just going to roll this up. Data equals PD. I'm using the Pandas package to read a CSV, and I'm going to put the link in there. And then I'm just going to press Enter to put a new line, because I have some other things I needed to put in, some parameters for this argument. So the delimiter in this case is actually not a comma-separated file, but it's a semicolon-separated file, if that makes sense. So you need to tell it to look for the semicolon, because by default, it'll look for commas. You can play around with this, and you see if you didn't put this, it wouldn't be able to read the data properly. We're going to do index column is the first column, so that it knows that will say like row 1, row 2, row 3. And then just to deal with NA values, which right now in the CSV, it's a period when it doesn't have a value, a missing value. But what we want is to actually make it a NA, not a number, not available number, missing number. So I'm going to tell it to take all the periods that are there and replace it with the actual not a number. So let's just run that, and we'll take a look. Oh, I missed something. I don't have a comma here, sorry. So there should be a comma at the end of that, because these are different arguments. That should read fine. And now we're going to take a look at our data. So how you can do that, just as a quick reminder, is you can use the head function, or the head method of a Pandas data frame. And this will give me the first 5, by default, rows of my data. You can see that what we're looking at, this is like, I think, some sort of MRI data with some IQ, a weight, height, and gender of patients or subjects. So you can see gender. These are 3 different measures for IQ, weight, height, and then some sort of MRI value. I'm sure this is vague, very vague, and not actually that relevant, but we'll see what we can get from this data. Okay, so that's always good to just take a look at your data. And what I really like is you can, so another thing, actually, before I'm going to add this here, just like summarize data. Using the dot summarize. I think it's, we'll see. I think it's summarize function. So what I'm going to do is use data. I'll actually put this a little higher. Is everybody okay with the first few lines so far? Because I'm going to move up. Okay. So data, and there's this function called data dot, oh, maybe it's pd dot summarize. Okay, maybe that doesn't exist. Okay, I don't know what I'm thinking about right now, but we're going to skip that for now. Okay, sorry. Yeah, I think it was that, but it wasn't automatically filling it out. So maybe summary. Yeah, right. Oh, describe. You're right. You're right. Thank you. Okay, so what this does is it takes a look at your data, and for all the variables in which they are numeric, it will actually give you like a good sense of like an overview of your data with the mean, standard deviation, the minimum, and the quartiles, and the max. So this is like a very quick look at just what your data looks like without actually having to plot anything. You just run one command and it'll automatically aggregate this data for you. And it's just a kind of a nice way to get a sense of what your data are. And of course, the best way is to start plotting. So we'll do that in the next little bit. But I feel like this is a really nice function. Like you can see if there's a lot of missing values. In this case, height is missing one value, weight is missing 2 values, something like that. If you had a ton of missing data, you might flag that as a reason to not include that column or something, right? It's a good idea to look at your data quickly in these ways. Okay, so the next question I want to see, so that was dot describe. So you have a data frame that you've already defined, and you can do the dot describe method on it. Okay, next up, we can just take a look at what the shape of our data is. How many observations do we have? So we can just do that by doing data dot shape, and you don't have, it's actually an attribute, not a function. So it just stored within this shape variable or attribute. And we know that there's 40 observations, 7 columns. So that makes sense that we saw the 7 columns and there's 40 variables there, data points there. Okay, so what we can do next, so I'm just going to correct that, sorry. We can check out one column by doing this. So this is kind of like an overview on Pandas just really quickly because we're going to be using these commands in the rest of the lecture. So if I do data and I just want to look at the gender, this is one way to look at, to pick one column and take a look at it. So you can run it like that, and you can see that the first subject is a female, then there's 3 males, et cetera, et cetera. But what you can do also is instead of data bracket gender, if the name of the column does not have any spaces in it, then you can just do a dot gender instead. So it's a little bit faster. Sometimes I prefer it just to use that. Sometimes it's just a little tip. But if it has spaces, you actually can't use it because you can imagine that would just break the syntax. Okay. So we're good so far. I know I'm going kind of breezing through this, but it's mostly just a data frame overview, and it'll be online also after. But I want to get into some of the more fun things. So the first thing we want to do is maybe make a group by object. So this is a very useful thing to aggregate data over groups of our data. So you can imagine that one group of this data are all the males, and another group of the data is all the females. There might be differences within these groups, right? In biological data, maybe their weights are different, their heights are different. You'd expect some sort of differences there. So what we can do to group our data is make a group by object. So we can do that by doing, let's call it data group equals, and then we have to do pd.group by. Just going to check, make sure I have this right. Okay. Group by, and we're going to group the very first, what it takes as an argument is what you're going to group by, right? What will you group by? So you're going to group by the gender column. So that'll group it into 2 groups, male and female. And then, so I made group PD, I didn't tell it the data. And it's actually on the object. So data.group by gender, sorry about that. So data.group by apostrophes and gender. So now that doesn't really do anything. It makes this object, but now we can start doing something with it, right? So what I can do also with that is, let's say I'm just going to make another, group, and I'm going to.
So it makes it an object?
So that's what group by does. It makes an object that I can act on, and I will show you what I'll do with it in this next bit. So check look at mean weight per group in data.grouped. So let's see what that looks like. So we have this data.grouped, which doesn't really look like much. And even if I actually do this right now, it's not going to show me something funny. Like it's a group by data frame object. Like it doesn't actually give me anything, but I can act on it by doing something like this. I want the weight So I'm just going to scroll up a second, but I'll come back just to show you something. So we have, So we have gender, so that we're grouping by gender, and we want to look at the weight. So you can imagine that it's kind of transformed this data frame such that we can do this, where I want to take the weight, I think it's capital weight, and then I want to take the mean of that, and it's going to automatically do it per group. So you can see what happened here is because I made this grouped data by gender, it'll give me the grouped weight, the mean weight, not just of the whole data frame, but per group. And you can do that for any of the other values like MRI count, which I don't really know what that's supposed to mean, but you see that there's some differences between gender and then maybe the different IQ values, which, and then height. Yeah. So that's just just like a quick way to look at the like aggregate statistics, like the easy things like mean, median. You can even, I'll just show you that really quickly, median. And mode, yes. I actually don't think mode is an option there by default, but mean is, and then max and min are, and I'll just do min. Okay, so those are just examples for you to see. But now what we've explored the data a bit. We get a sense that there's maybe gender is going to play a role in some of the different values here, but maybe also the MRI count will be influenced by the IQ, or there's many things that could be going on. So one quick way that we can take a look at correlations between our data and the different variables there is by plotting a pairwise scatter matrix. So if you don't know what that is, we're going to see really quickly. But before we do that, we need to get some plotting tools from Pandas. So I'm going to do from Pandas, import plotting. I kind of wrote that backwards. But anyways, yeah, so that should be that. And then I'm going to be able to use the plotting.scatter matrix function. And I'm going to give it, let's see, data of, so I have 2 square brackets because first it's telling it that I want columns and I want to give it a list of columns. So that's what the 2 square brackets will tell you. So I want weight, whoops, height, and MRI count. So I'm just going to take a look at the first few interactions potentially. Oh, sorry, I'm just going to put a semicolon there so that it suppresses all those outputs. And it'll just give me this plot here. So what's happening here is we see that for each of the things that I asked, each of the variables of which I asked for, it's going to plot them against each other in a pairwise manner. So here it's MRI count versus weight, MRI count versus height, MRI count versus itself. So when it's with itself, obviously it can't make a correlation with itself. It would be a perfect line. So what it gives me instead is is a histogram of the data. So it's a nice way to visualize your variables. So you can see here that maybe there's a relationship between height and weight. That makes sense. Maybe the taller you are, the more you can weigh. But MRI count, you see that there might be some correlation between weight. There doesn't seem to be much of a correlation in height. So this is just like a quick way to take a look at your data. This doesn't seem so meaningful right now, but you can imagine in your own data. So throughout this lesson, I want you to think about your data. Like, what could you apply these functions to that would make sense for you, right? So this is a really good way to take a look at the distribution of your data as well as the relationships within your data that are already present. You might not even realize that, you might not think that 2 things might be related to each other, but when you plot it, you see that they're just very obvious, right? And we can do about some statistics later on whether or not they actually are linear or related, sorry. Okay, so next thing you want to do is just do the scatter matrix on the other 3. I guess we can just use the same. Can copy that. And instead of weight, height, and MRI count, we can do the other 3. So I'm just going to change these like that. The IQ, I'll just bring this up. And I think it's FSIQ. Should make another 3. And don't forget the semicolon if you want to prevent all those output lines. And so again, we can get like this. So we can see that maybe these data, there are some correlations between the different measurements of IQ. I don't think it described necessarily what the difference between the PIQ, the VIQ, and the FSIQ is, but yeah, there are some relationships there. Okay, is everybody good with that? So this is kind of like the concept of just looking through your data, plotting some things, getting a sense of what relationships might already exist without having to do any stats yet, because it's important to like know where to go. You can run a million stats tests, But if you don't have a lead, if you don't have a hypothesis to test based on what you see, then you might take a long time to analyze your data. Okay. So next thing I thought would be good is to plot and compare some distributions. So we've seen some distributions already. So we see these histograms within the center. But what if you just want one histogram or compare specific histograms to each other? So what we're going to do with this is first import another plotting package. So I was using the Pandas default plotting methods that works upon its data frames. But another really powerful tool for Pandas data frames is Seaborn. What we can do is import Seaborn as SNS. So that's just the default kind of way that we name it or nickname it, I guess. So I'm just going to import Seaborn, sorry, SNS. What we can do is use it to plot a density plot, basically, or a histogram. Or it's a density plot, sorry, but let's look at it first. So you can use SNS KDE plot. And what I did right there is just Alt tabbed to complete, just because if I start with a K, I can tab. Oh, that's the only K. It's not a good example, but let's do L. And if I tab, it'll show me all these options that I can use with a Seaborn, right? Like, for example, I might want a line plot or something like that. But if I do a K, the only option is KDE plot, and it finishes up for me. And what we do is we can take a look at what it needs. So what I just clicked right now is Shift Tab, which will show you the documentation for that code. And I can scroll around in it, and it has like examples. It tells me what all the parameters are, tells me what parameters are necessary, which ones are, what the defaults are, and then some examples, I think. Yeah, so it has some examples here. So I think that's really useful if you're using Jupyter Notebooks, is you can shift enter it within the parentheses of a function, and it will show you these things. So just to remind me what we need the data, which is going to be data, and I want the FSIQ, right? So remember, that's how we get one column, the FSIQ. But if I want to plot the PIQ on top of that same data frame so that we get it all in one image, I just make a new line. And then I just do the same thing using the data, but this time PIQ. And the same thing, I'll just do SNS.kde plot data and apostrophe VIQ. Okay. So I can run that. And again, if you wanted to like suppress these outputs, I actually don't know if this is possible, but I can try. Yeah, sure. And now it plots all the three distributions on top of each other, the three density plots on top of each other. There's a legend in the corner to show you. So you can start to get a sense if maybe there are some inherent differences in your measures, right? Okay, so these are density plots. You can also make histograms and commute. So I'll just do the histogram first. So I'm just going to take the same 3 lines of code, because that's what coding is all about. You just use the same code over and over, and you make little changes incrementally. At least that's how I think of it. And then I think, what was it called? So instead of a density plot, how do I do this? Let's just do a cumulative instead, density plot. So cumulative equals true. I'm just gonna, again, copy that and then do it 3 times. So I don't have to, so I can be lazy. Okay. And then let's see what we get here. Is instead now, you just with one change of what you already wrote in your code, you can make a totally different plot with a cumulative density plot. Okay, so that's just kind of like the overview of the plotting and exploration of data section. There's so many more things you could do, of course, right? So take a look through the documentation of Seaborn. If there's a type of plot you want to see, just look it up. And the documentation is really great for that package, so I highly suggest looking through it. And there's also a website, I think it's called Python Graph Gallery, which you can look through to see what kind of graphs you want to make, and they'll show you a ton of example code on how to do it. So that's just an offset. I think it's Python Graph Gallery. Yeah. Okay, so let's do some hypothesis testing, which I think people are why you sort of may have come here. Okay, so the first thing, I guess I forgot to take this out, but we're going to import from SciPy, import stats. So just type this in, because SciPy is going to have a lot of the stats functions that we're going to use. So one thing that's very different from Python and R is R was written to be a statistics language, whereas Python is meant to be general purpose. And so it has packages that have stats modules in it, but it wasn't necessarily, to do it in base Python would take a lot more work because those functions aren't built into the code, right? It wasn't meant to be for statistics. But there are packages that people use that have a lot of the things you would use in, say, R. OK, so does everyone have that? OK. So once I'm going to run this, because I don't think I've run it yet. So now I should have a ton of examples to a ton of functions that I have access to now. So first, you might want to do like t-tests, right? The simple t-test that basically most biologists will often use. So in a one sample t-test, you're testing the comparison of whether the average value or the value of a population mean differs from another value. What is your hypothesis? Maybe I think that this population of people will have a height greater than say 5 feet or something like that. And then it tests how far away it is from that, from the number that you give to the t-test. So as an example, we can test this IQ and against the mean of 0. Sorry, let me just read this over. Tests whether population mean of data is likely to be equal to a given value. So is it greater than or less than statistically than the value that you're testing against? So if we run this test, we're going to use scipy stats.t-test one sample. So I'm just going to type along with me. So just going to give, let me just check. OK, so let's just do stats.t-test underscore one samp. And then data equals VIQ. So I think this would be less commonly done because typically you have two groups that you might want to compare, like a control group versus a experimental group or something. But it's good to know these different things. So let's say it's 0, compared to 0, and then we can press enter, and it should print out this statistic. So you can get this is the value of the statistic, but and then the p-value will tell you. So this is very negatively, like a very small value. It's like 1 to the negative 28. So you can imagine that this the VIQ of the data is definitely the mean is definitely different from 0. So people don't have 0 IQ in this case. But that's probably a less interesting thing that you'd want to do. So typically what you'd want to do is test for a difference across populations, right? So again, what I said before, like a control population versus a disease population or some treatment population where you're giving them some drug. So so in this case, we're going to test whether the VIQ is different in the male and female populations. So what we might do is set up 2 different series for the female and the male to compare. So what we would do is, let's do female equals data such that data.gender, so we only want the female, right, is female. Whoops, sorry, I need quotes. And we only want the VIQ column. Okay, so does this sort of make sense? You're taking, of the data, take the ones where the gender is female, and then take only the VIQ column of those columns, of those rows. And then for the male, in this case, we can't use group by because that will aggregate over it, and we need the individual data points to do a t-test, right? So I'm going to do a male series, and it'll be the same thing, except I'm looking only for the data where the gender is equal to male, and the VIQ in this case also. I'm just going to run that, and then I'm going to run use the stats test on this. So stats.t-test. And then this is a little bit different. Instead of one samp, it's IND for independent. I think it means that they're independent. And I'll explain the independent part of the next bit. And in there, I would put the male or female. It doesn't really matter the order in this case, but I'll put female and then male. And then it should print out that there's, as we hope and expect, that there's not really much of a difference between male and females on the IQ score. So it's, well, based on the p-value, there's not, it's a very, the means are pretty much similar. Okay, so if we wanted to look at, so I'm just gonna leave this up for another second while I talk. So if we want to look at comparing the PIQ, VIQ, and FSIQ using for the same individual. So let me think how I want to say this. So if we wanted to look at the FSIQ and PIQ using a two-sample t-test, we could do that by using a two-sample t-test, right? So let's just do it first, and I'll explain what I'm getting at in a second. So we'll use the same format that we did here, except that we'll just do it on the FSIQ and the PIQ. We don't need a group on male and female at this point. We're just looking at the two columns. Is there a difference between FSIQ and IQ of people, right? So we'll just do stats.t-test independent, I'm sorry, I'll move this up, of data of FSIQ. And then the second thing that we're testing on is whether the PIQ is different than the FSIQ. So it tells us that it's not really statistically significant. But the problem with doing it this way is that it doesn't account for the fact that these measurements are taken within the same people, right? So imagine this person took a test on, took the FSIQ test and the PIQ test. There might be individual differences within each person that might be canceled out by taking an independent test. These values are not independent. They're within the same person. They're paired. So what you actually want to do is do a paired t-test, right? So this is why you would not actually have to do this, because it would not make sense to do that. You'd be losing any of the individual differences in the data. So what we can do here is the test REL, where the data is related. So let's do that. So stats.t-test underscore REL of the same thing I put here. So data square bracket FSIQ, comma data square brackets PIQ, and then I think I'm missing something. Oh, I have two brackets and missing, a bracket there. I see where it came from. Okay, and then now you see that there is a difference between FSIQ and PIQ when you account for differences within an individual. And what you might not realize is that this is actually the same as a one-sample t-test on the difference between the FSIQ and PIQ. So if you take the difference and then compare that to the mean of 0, then you'd see that this is actually should give the same result. So let me just check right here. So let me move this up. Is everyone okay with what we have so far? Okay, and remember this will be online. So if you're missing some things, you can just kind of follow along after. So stats.t-test underscore one samp, yep, data of FSIQ minus data of PIQ. So this should just end up with one value, right? Because you're subtracting across every subject. And you're comparing each of those values when you do the t-test to the mean of 0. And you see that it should give the exact same values, 8.082 and 1.78. So it's just like something you can do it different ways, right? So it's just showing you the different ways you can do this. These tests assume normality in the data. And so this we covered a bit more in last week's lecture. We won't go too much into that. But a non-parametric alternative is the Wilcoxon signed rank test. And so the stats package also has that ability too. So if this data is not normal, then you can use the stats.wilcoxon bracket. I think you can do the same.
Is there a test? Is there a way to test normality?
Yes, it would be I think there's I can't remember what the 3 tests are. There's 3 different ways you can test it. I don't know them necessarily, but they are available in the same package as this, and you would just look it up, and then it would be able to. And then there are different reasons why you'd use each one, and that's I think what Tomas got into a bit more last week. But there is definitely you can test whether things are normal. But if in case that your data is not normal and you want to use a non-parametric test, it would look similar. It would be FSIQ and then data of PIQ. So then again, these relax the restraints for needing to have normal data, and you see that the result is going to be different because it doesn't have these assumptions underlying the test. Okay. And there's just a note that there's another one for the non-paired case. So this was in the paired case. So for the independent case, you would use the Mann-Whitney U, just as a note. So, okay. So that's just an overview of the t-test section, hypothesis testing. If you have very simple 2-group data, or you compare, or 1 group to a hypothesis that you have. But what you'd often have is that things are complex and they have multiple factors influencing the results that you see. And so I'm just going to kind of get a little bit faster. I think we have 20 minutes left or so, or 15. So I don't have too much left, but we'll go through this. So given 2 sets of observations, X and Y, we might want to test the hypothesis that X and Y are somehow that y is a function of x in a linear sense. So we can use the stats model to test the linearity of this. And the simplest way is to use ordinary least squares. That's just the method that the method used. I don't know too much about it, but first what we can do to try this out is make some code, make some sample data that we know we've generated it to have a relationship that is linear, right? So we don't want to test whether this works in this case. So let's just import NumPy because that's what we'll use to generate this data as NP. And I'm going to create a range of 20 values over -5 to 5 using NumPy linspace, and I'll call it fake data, because that's what we have here. Fake data is equal to numpy.linspace, and it's going to go over the range of -5 to 5 and take regular intervals, because we're just making our x values, right? They should be regularly spaced, and we'll take 20 of those. So that's sort of what this function's doing. Okay, and what I want to do is set the random seed to 0. So what that does is it's going to have a random number generator in the next step. I just want to make this .seed, make this consistent so that if I run this again, you'll get the same result. It's just for the reproducibility methods, right? Okay, just so that we should get this. Well, I don't think we'll get the same result as each other. Wait, will we? I think we will. No? I think it should be the same for all of us, but it might depend on like your computer itself. Okay, so then now we're going to generate some data, some y data. So actually, I'll call this the x. I'm going to change fake data to x, just keep it simpler, and we'll call y is equal to, and then we'll make our function, right? -5 plus 3 of x plus 4. And then this is the random component where we're going to add a bit of noise to the data, just so that it's not completely linear. Random.normal, and it's going to be normally distributed. The size is x.shape. So just give me 20 value. For each of these x values, jitter it by a little bit, add some noise. That's what that little step is doing. This is just generating the data. It's not too important, but just to see, just so you understand a bit of what we're doing, and turn it into a data frame. So I'm going to call this I'll call fake data, is equal to pd.dataframe. I think I'll give it, so that's those are curly brackets to start a dictionary, because that's basically what a data frame is. It's a dictionary, but looks nicer. And for the x component, we'll call it x, and we'll give it x. And then for the y component, we'll call it y, and we'll give it y to be its values. Does everyone see that? So this is a lot, I know, so I'm going to leave it up for a little bit. And then if you have any questions, let me know about what step is confusing. So this is just going to generate a data frame, just like the nice ones we've seen before, except that we generated the data ourselves instead of reading in a data frame. So I'm going to run this. Hopefully there's no problems. Times x, sorry. You should, no, that Pandas has no attribute data. That's a capital F. Okay, that should be all the errors that I get. So if you're getting some errors, maybe you put your hand up and then maybe one of the helpers will come through. Okay, because I know this is a lot of code. So the first thing we're going to do is import from stats models dot formula dot API. I'm going to get import an OLS function. Okay. So this is a little bit long, but it's from stats models dot formula dot API import OLS, and OLS will be the ordinary least squares, which will do the linear fit on this. So we're going to specify a model, which we'll call a model is equal to OLS, and what it takes is a function. So we're sort of like specifying what we're actually interested in, and we'll do y by x. So y is related to x somehow, and we're going to try to fit that. And the data we have is called fake data, and we're going to do dot fit on it. I think this is all we need to do. So you run that, shouldn't give any errors. We've saved the data, the results in the model, and then we can inspect the results of the model using model.summary. Oh, sorry, I didn't spell that right. And I'll just wait. I'll leave this up for a little bit, and then we'll look at what the data is. Does anyone have any issues right now? I can come around really quickly. Okay. Okay, so if you got to that, then model.summary should give you the results of your fit. And you can see that what the R squared is about 0.8. So you can see it's pretty related in a linear sense. You get an F statistic, a probability F statistic saying like how, basically your equivalent of a p-value, right? So this is like a really simple case where we know that they're going to be related. But what happens if, is everyone okay so far? Model.summary is going to give us the results of that. Okay. And then it gives you the intercept, like the actual things that you might be interested in, like the intercept and the t-value and the x. Really, yeah.
Stats models is its own package?
From stats models is its own package. Yeah. And then you just need all these, it's just submodules within that package. Yeah.
But it's additional models beyond.
Side, yeah, exactly. Yeah, but it should be included in.
No, I just had to install it.
Oh, you did?
Yeah.
Oh, darn. Okay, sorry, I didn't realize.
It worked after I installed it. Yeah.
Okay, great, sorry. It might be depending on the version of Anaconda, maybe the more recent one doesn't include it necessarily anymore. Okay, sorry about that.
Oh, sorry, can I just
Oh yeah, sure.
Thanks.
Yeah, I'll just leave that for a second. And then in this last bit also, I'll print. You want the parameters on its own. So before we had to read the summary to get the y-intercept and the x, the intercept and the x coefficient, then you can just get it by typing print model.params as well. I'm just going to run that and I'll print that there. So the intercept is -5 and the x is 2.93. Okay. Okay, so that covers basically the simple linear case. But what if we have categorical variables and we want to compare groups or multiple categories? So not just one thing against another thing. So let's remind ourselves what our data looks like by using data.head. So we're going to do data.head, this gender, FSIQ. So it looks sort of like this. So if we want to write a comparison, we want to see if the VIQ is related to gender. Sorry, let me just get this down. Using a linear model. So we've already done this using the t-test, right? But now we want to see if there's a relationship using the linear model. So we can do this by doing OLS. Sorry, I'll call it model equals OLS old. And then we want to look at VIQ. So this is like the function part. So this is very similar to the R syntax, where you have like a function that you like a string of things that tells it what to look for, and then you give it the data that will look for these column names. So we're looking at VIQ related to gender, and I'm going to give it the data. I mean, we already know that it's not statistically, there's no difference, but just showing that there's multiple ways you can do this. And then just as a side note, OLS automatically detects that gender is a categorical, so male and female. But if, say, you had numbers like a dosage, like the dosage of 10, dosage 20, dosage 30, and you want to treat that as categorical, you could do that by putting this like C, almost like a very R syntax, where C for categorical, bracket gender, just to make it like a factor is equivalent. Okay, so I'm just going to run that, and I'm going to also do model.summary again to get the results. So if we go up a little bit, we see that the R squared is pretty low. We see, so as we know, the results there should not be any effect. And if we actually run, so if everyone has that data, if we compare these results to the t-test that we ran before, it should be exactly the same, right? It's just using a similar method, except it's a linear model, a different method to get to the same answer. Yeah, sorry. So this is what we're actually interested in. This was just to show that if we wanted to make something a categorical. But in this case, gender is already strings of words, right? So you don't need to actually make it a categorical. Okay. I might skip over some things just to make sure we cover everything. So what I might skip to after this part is just, we can come back to it if we have some time, but let's just jump into doing an ANOVA, because what we often might have is multiple groups that we want to compare the values for, and it's not just one group versus another group. You might have 3 groups or multiple interactions of different variables, right? So I'm just going to skip over some of these things. Okay, it's not too much that I'm skipping over. So it'll all be online anyway, so you can look back on it. So first we need to read in our, so I imported some iris data, but that will be the second link. So if you can go back to that other that page, the events page, I'm going to get the second link, which should say iris.csv at the end. Copy the link, and we're going to read it in. I'm just going to call it iris equals pd.read csv. And there's nothing funny here. You can just read it as is. It's going to be commas separating it, and there's no NA's values. So we're going to run that. And let's take a look at what iris looks like. I'm going to do the head function. So we get the name tells you the species of iris flowers, and these are all different measures such as sepal length, sepal width, petal width. So we might predict that some of these features might predict what, by looking at the features, you can predict what species something belongs to. And we can see how these different features interact in the different species. So first, we can just visualize the different species and their sepal length in a box plot using the box plot function. So we can look at, so using Seaborn, which we already have, we can do the box plot function. Let's make sure it's right. And then we can look at one of the features like sepal length. So first, on the bottom row will be name. So I can just do this, his name. Y, so it will be the sepal length, and the data is equal to iris. So sorry, I'm just going to do this again. You can see here that you can see the three different species. They have very different means in terms of sepal length. So that might be something that you would immediately just say, maybe there's a difference there. It seems like there's a difference there, but we want to actually test this, right? So how you do this is use an ANOVA, a one-way ANOVA anyways. So we have this plot. I'm just going to wait for a second in case anyone's still typing. No? OK. So in order to actually use, there's two ways I'm going to show you how to do a one-way ANOVA. And the first way is a bit more straight intuitive. It makes more sense, but we'll see that the second way is way faster. So I'll just split. So first thing we have to do is split our data into the three different species. So I'm going to make a Setosa. So sort of like when I had the female group and the male group, here I'll do a Setosa group, a versicolor group, and a virginica group. So Setosa is equal to iris, where iris of name is equal to, so there's an outside bracket and then an inside bracket for each one. Where iris name is Setosa. And because I'm, as usual, I'm quite lazy, so I'll copy that. And then I'll just change this to the next one, which is versicolor. And the name there is versicolor. Same thing here. I'll do the same thing for virginica. Virginica. OK, so I'll run that. So we split the data like this. The reason is because the stats, which we've already imported, so it's a new function in stats called stats. Oh, you're right. You're a good point. So then, yes, at the end of each of these, you would have sepal length. Thank you. And here again, sepal length. Again, only want the sepal length column. OK, sorry. So we can actually take a look at what one of these looks like. It should just be a ton of values for the sepal length for only Setosa, right? OK. So we're going to use F. We're going to get an F value and a P value from our ANOVA. It actually will have more values. Actually, this is all that will be output from this version of the ANOVA. But we're going to use stats.f one way. And then within it, I just give it each of these. So I want to test the difference between Setosa, versicolor, or test if there is a difference in these means. And then I can print the results. Value and P value. So you get these values. You can see that the P value is very significant. There is some sort of there's something going on here between species. There is a difference between sepal length, which is what we visualized with that box plot. But it's good to see that it's actually there. Statistically significant, very, very much so, actually. OK, so that's kind of like the longer way to do it, mostly because we have to split up our data. right? But it's very obvious. It's very intuitive to see what you're actually doing. You're giving it these groups and it's comparing. A more simple way, which will be through the stats models. And I think if you guys, yeah, does everyone have stats models now? You sort of, okay. So we can try importing from stats models.api, import SM. And I think we already have our OLS, but I'll do it also. Sorry, import SM and OLS. I think that should be, cannot import name. API, stats models API, import SM. Oh, because these are not from the same one. Okay. Okay, let me try this for a second. Oh, I see. So instead of, I'm actually going to import stats models.api as SM, sorry, for stats models. And then from stats models.formula, which we should have this, but I'll just write it again for posterity. Import OLS. Okay. The next thing, I'm just going to run this to check. Okay, so that should be good. If we get that. Okay, so this is, we're going to do the exact same thing that we did before. Like the result should be the same. But what we're going to do is specify a model similarly to what we did before with the linear models by doing model is equal to SM dot, sorry, OLS. We're still using the OLS method. And then what we'll give it is a sepal length. And then we want to see if there's a relationship between the sepal length and the 3 different named groups that we have. And the data we have is called iris. So this looks pretty familiar, right? We've done this already, but now we can use it to actually run an ANOVA and fit that. And then what we do, what the interesting part is what we use SM to make an ANOVA table, which will print out the results for us. So AOV table.
What does the tilde do?
The tilde sort of, it does, in this case, that's their formatting, like not a Python thing. This is their formatting for saying that there's a relationship that you're looking for between sepal length and name. So that's just their way to say that this, they could have chosen to put like a plus or anything else, but that's what it's indicating. And in this case, I'll talk about that a little bit more in a second. But first, I want to get to the AOV table, which we can do by doing is sm.stats model stats.ANOVA LM. So this tab completed there. And what we do is we give it the model and we tell it it's a type 2. The reason is, I think in this case, we're not looking at any interactions. So if you know with an ANOVA, you can have things that, groups that have an effect, whereas groups that that are interactions between the groups that might cause an effect that you see. So in this case, there's no group that there's no interactions between groups. They're only looking at name. So we don't actually need to do a type 1 or type 3. So type 2 is for this case where there's no interactions. And then we can print the results. AOV table. That should be it. So I'm going to roll up a little bit. And it should be the exact, so if you actually look, these are the same results. And this one is just that we have to specify an OLS first, a linear model. Then we print it an AOV table. But we don't actually have to split the data into the 3 groups. So it'll automatically do that for us, right? And then after this, you can do your post hoc tests, like your 2GAze HSC and all these, or whatever other tests that you want to run on your, once you find that there is actually an effect or an interaction. So I don't have it specifically in this data, in this Jupyter Notebook, but if you wanted to do like a 2-way ANOVA where there's multiple things that could be impacting your results, you could do sepal. Let's work on our original data set. So I'll just say move down. So let's say our model is equal to OLS. And instead of, so if we look at our original data, we had gender, so let's see if FSIQ is related to gender, as well as plus, as well as MRI count. And then we want to look at the interaction between these. So this is the plus just tells more things that you're adding to the interaction, and then this colon sign means that there's an interaction, if there's an interaction between these two. MRI. And the data is data, which we already had. I'm not sure that this will work necessarily. OK, and then we can do the AOV table on this. And in this case, we do have an interaction, so we cannot use a type 2. I think the type 1, type 2, type 3 have different assumptions, and type 2 assumes that you don't have any interactions, whereas type 1 and type 3, I think type 1 is the most stringent. So it's always good to start with that. And then we can read more about that, but I think that's a different lecture. We can print that out, and we can see again. So the results here are saying that there doesn't seem to be an effect of gender or MRI count on the but there is one of MRI count on FSIQ, and between gender and MRI count, there doesn't seem to be any interaction between them on the final FSIQ. So depending on your data, you'll have different ways to construct these ANOVAs, right? But in this case, it doesn't make sense that gender would impact the MRI count and then impact the FSIQ, since there was no interaction in the first place. OK, so that's basically all I want to cover. There was a bit more, but I think it's just extending upon the OLS, which could be really powerful depending on if you have multiple variables that you want to plot. It's not just like one, it's a polynomial fit as opposed to just a single fit. So does anyone have any questions about this so far, or in general about stats in Python? So I've only just given like a brief overview. But the thing I'll just close with is saying, if you just want to do stats and you have your data and you just want to do the stats on them and get the really rigorous and easy stats, you should probably use, I would say you can use R, and it would make more sense because it has a lot of the tools for all the different stat sets you want to use. But in the context of using Python in a pipeline with all your data, so say you do image analysis with your data and then you bring it into some sort of pre-processing, and you do that all in Python, it makes sense to then continue using Python for your stats and then end up doing your plotting and doing all that other stuff. So that's just kind of my personal opinion. But I find that it makes sense for me because I use a lot of Python anyways. But I do agree that R has a way more powerful stats packages for different types of things. OK, that's basically it. Thanks, guys.